going to talk about graphing functions that you've learned in your past. It's really important to do a review today so that you remember how to graph each of these functions, because we're going into piecewise functions, which uses all of these old skills you should know already. Okay, so linear functions. The parent function of a linear line would be y is equal to x. And I'm going to graph that right here. And if y is equal to x, it's just a straight line like that. So if x is 1, y would be 1 because they're equal. If x is 2, y is 2, and so forth. Okay. The domain would be all real numbers. So in interval notation, it would look like that. Your range would also be all real numbers. Okay, for the parent function. Now, the child function that is going to be translated 2 units up would mean that we would take y is equal to x, and we're going to add on the outside plus 2. All right. If we want to translate it down 1 unit, then we're going to subtract. I need an equal sign. We're going to subtract 1. And that would shift the parent function up 2 or down 1. Now, 3 ways to identify a linear function are the following. There's always a constant rate of change, meaning that your slope is constant. The x variable has a positive 1 exponent. So usually you just write that as x, but realize that x cannot be in the denominator either, because that would actually be x to the negative 1. The graph is a straight line. A real-life example of a linear function would be Haley gets paid $50 a day plus $5 for every shirt she sells. So if the amount she gets paid in a day is equal to y, that would be $50 plus the $5 for every shirt. Okay, slope formula, y2 minus y1 over x2 minus x1. You can think of it as rise over run or change in y over change in x. Slope-intercept form, y equals mx plus b, where m is your slope and b is the y-intercept. Okay, and then point slope form would be y minus y1 is equal to m times x minus x1. And you can use this when you have your slope and you have 1 point, which would be your x1, y1. All right, so if we were to graph, let's graph y is equal to negative 3/5 x, and we'll say plus 7. We would start on the graph at 7, and then this is your slope, and you would go down 3 to the right 5. All right, and you all know how to do this, so let's move on from our linear functions into quadratic functions. So the parent function of a quadratic is going to be y is equal to x squared. You know that it's a quadratic because x is raised to the second power. You're going to end up making on your parent function a parabola. So the vertex of your graph will be at 0, 0. And if you're going to think of it as a quadratic, if x is 1, well, 1 squared would also be 1. Negative 1 squared would be 1. And then 2 squared would mean you would go up to 4 because 2 times 2 is 4. And negative 2 squared is also 4. So you make this symmetrical graph that turns into a U, because when you get to 3 and you square that, you end up going pretty high. You go to 9. So it's about right here. And then negative 3 would also be squared to give you 9. So you have to make sure this does not look like a V. It looks like a parabola, a U shape. The domain of the parent function would be all real numbers. The range of the parent function would be, we would be at 0, and actually it would be a bracket. So we'd have 0 to infinity for the parent function. Okay, if we wanted to take this and wanted to make it wider, what you would do is you would actually multiply the x squared by a fraction. This would actually be called a shrink. Because when you take that parent function, let's say this is the parent function, and we make it wider, it's like if you were pushing down on the top and bottom and flattening it out, you're shrinking it. Okay? We want to take this function and make it narrower, then we would multiply the x squared by a number greater than 1. So let's just multiply it by 2. And if this was your parent function, what's going to happen is that your vertical jumps are going to go up by 2 times the amount they normally would. So this is called a vertical stretch. And technically this should say a vertical. We should write vertical here. Vertical shrink on the left side, because you could have a horizontal stretch and shrink. 3 ways to identify a quadratic function are the following. You have a graph that has a U shape known as a parabola. X is raised to the power of 2. So we have x squared. And the graph has a line of symmetry, also known as the axis of symmetry. A real-life example of a quadratic function could be a baseball being hit and landing in the outfield. So it would be hit, and then it would land in the outfield. Okay, standard form would be y is equal to ax squared plus bx plus c. If we want to find the axis of symmetry, or the vertex, which if we're looking at this graph of the baseball, the vertex would be the highest point. It's the maximum point. If you had a graph that opened up, the vertex would be down here. But that axis of symmetry would be the line that is vertical and goes through the vertex. So the axis of symmetry, you're going to use negative b over 2a. Your axis of symmetry will be x equals that number, and that's that vertical graph. Now to find your vertex, and I'm going to do a problem like this with you, but to find the vertex, you're going to start out with x equals negative b over 2a, and that will give you your x coordinate of your vertex. To figure out the y coordinate, you're going to plug in your x coordinate into equation. And then you'll end up with whatever y is. So let's do one like that. I'm actually going to make it a harder one, and we're going to have y is equal to negative 2x squared plus 4x plus 3, so we can remember some more of the rules. So to get the vertex, the x coordinate would be negative b over 2a, which would be negative 4, because remember this is a, this is b, and this is c. So negative 4 over 2 times negative 2. So then you have negative 4 over negative 4, which goes to 1. So for the vertex, our x coordinate is 1. Now to find the y coordinate, it would be y is equal to, you take your equation, negative 2, and instead of writing x squared, we'll write 1 squared. So we're substituting the x into the equation, plus 4 times 1 plus 3. So here, 1 squared is 1, times negative 2 is negative 2, plus 4 plus 3. So for this answer, we end up getting 5 for the y coordinate of the vertex. Now to graph this, we would go over 1 up 5, and we'd have to look at the equation. The equation has a negative 2 as your a. The negative means that it's going to open down, and the 2 means that it's going to be a vertical stretch by a factor of 2. So usually you would think of, oh, I'm going to go to the right 1, down 1. But that's not going to be your point, because you have to vertically stretch it by 2. So instead of vertically going down 1, we're now going to vertically go down by 2. So it'd go right 1, down 2. And remember, this is your axis of symmetry, so it'll be symmetrical on this side. Left 1, down 2. For a parent function, if it were to open down, you would go to the right 2, down 1, 2, 3, 4. That's not going to be correct because we are vertically stretching it by 2. So instead of dropping down 4, we're actually going to double that and drop down 8. So for our second point, let's get rid of this one. We're going to go to the right 2, down 8. And that's actually right there. So then you can start to draw your parabola, and you'll have a symmetrical point on this side, and that would be the graph for that equation. Sometimes a quadratic equation is given in factored form. So if we had y is equal to 1/2, and we'll do x minus 6 times x plus 2. So this is a quadratic because if you were to FOIL it, x times x would give you an x squared. Okay, so let's graph this. First, if we're going to find the x-intercepts, that's when y is equal to 0. So if we make this equal to 0, well, 0 is equal to 1/2. We don't deal with that. 0 is equal to x minus 6, and 0 is equal to x plus 2. So your x is equal to 6 and negative 2. So when you go to graph this, we have, let's make that a little straighter. We have, let's go by 2, 4, 6. So we'll have a point here at 6, and we'll have a point here at negative 2 for our x-intercepts. To make it more accurate, let's figure out the vertex. The vertex is going to be in the middle. So for the x coordinates specifically, we have, let's do this. We have negative 2, 0, and we have 6, 0. So to find the vertex, our x value is going to be in the midpoint of negative 2 and 6. So negative 2 plus 6 divided by 2, well, that's 4 divided by 2, that's 2. So our axis of symmetry is going to be x is equal to 2. That means that our vertex is going to fall on that line somewhere. Okay, well, to figure out the y-coordinate, we're going to just take positive 2 and plug it back into the equation. So y is equal to 1/2, and then you have 2 minus 6 times 2 plus 2. Well, this goes to negative 4, and this goes to 4. Negative 4 times 4 is negative 16 times 1/2. You have an x or y coordinate of 8, and it would be negative 8. So you have a y coordinate of negative 8. So 2, 4, 6, 8. That would be your vertex. And usually, if you have 3 points to draw your quadratic, you're good to go. One more form of a quadratic equation that may come up, and I'll put it up here, would be something that may look like this. Y equals negative 1/2. We'll do x plus 1 squared plus 3. And this is called vertex form. And if you were to graph this, the formula for vertex form is y is equal to a times x minus h squared plus k, where the vertex would be h comma k. So the vertex for this equation would be negative 1, positive 3. And so if you were to graph that, we would start at negative 1 and then up 1, 2, 3. That would be your vertex. That'll be your axis of symmetry. X equals negative 1. And then it is going to be a vertical shrink by a factor of 1/2 because of the negative 1, or because of the 1/2 in front. And the negative sign means that it's going to open down. So usually for a quadratic, you go over 1 and then up 1 or down 1. In this case, we're going to go over 1 to the right, so we'll be right there. And then instead of going down 1, we're going only down 1/2 because it's multiplying by 1/2. And then you usually go over 1, 2. So right here, down 1, 2, 3, 4. So normally, if it wasn't a vertical stretch or shrink, you would go there. but we have to shrink it. So we're going to multiply the vertical jump of 4 by half, which means we'll only jump down 1, 2. So that will be where that point goes. That will be the right side of your parabola, and then the left side will be symmetrical. So it goes over to the left 1, down a half, over to the left 2, down 2. And that would be a quadratic equation using vertex form. Okay, moving on. We have exponential functions. The parent function of an exponential function would be y is equal to b raised to the x power, where b is greater than 0 and b cannot equal 1. Because if you have a base of 1, 1 raised to the 4th power is 1, 1 raised to the 10th power is 1, you wouldn't have an exponential graph. The domain, so first of all, before we do that, let's graph our parent function. Okay, when we have, let's make b 2. So we'll graph y is equal to 2 to the x power. Okay, well, when x is 0, that means that y is 1. And every exponential graph, exponential function will go through 0, 1 as long as it hasn't been shifted up, down, left, or right. Okay, so then from there, if I made x1, when x is 1, y would be 2. When x is 2, y would be 4. And if we made x negative 1, you would get 1/2, because remember, that would make it as 1 over 2 to the first power. And if x was negative 2, that would be 1/4. And remember, with this parent function, it's never going to go below the x-axis. So that would be a parent function if the base was 2. So the domain of the parent function is going to be all real numbers. So the range of the parent function would be greater than 0 all the way to infinity. And realize that we are not including 0 in the range. It's going to be above there. All right, let's write a child function that is translated 2 units up from the parent function. That would mean we'd have y equals your base raised to the x power, and we're going to add 2 to go up. Well, what if we wanted to translate 3 to the left? Let's just do a quick review. If we had quadratic, y equals x squared. If I wanted to go 3 to the left, I would do y is equal to, and I wouldn't subtract 3. First of all, you're going to add 3. Now, if I just did it like this, that would mean 3 up, so that doesn't make sense. What you're going to do is you're going to add 3, but that will be part of what's being squared in a quadratic function. Okay, the exponential function is a little bit different. So left and right do the opposite signs of what you think. Left is addition, right is subtraction. So this would be y is equal to b raised to the power of x plus 3. Okay, so the plus 3 gets added into the exponent. If it's up and down, it gets added outside. If it's left and right, it gets added to the exponent. Okay, ways to identify exponential functions. An exponential function looks like half of a U shape. It does not have a constant rate of change, so your slope is not constant, and the variable is in the exponent. A real-life example of an exponential function would be Brian puts $1,000 in his savings account that earns 2% interest compounded yearly. Okay, how do you know if a function represents growth or decay? Well, if b is greater than 1, it's growth. And if b is less than 1, then it's decay. And what is the compound interest formula? We don't necessarily need that for piecewise functions, but there it is. If I were to give you, we already did y equals 2 to the x power. If I did y equals 2 to the, let's write, x minus 3. That means we're going to take our parent function and move it. This means 3 units right. Okay, so usually we start at 0, 1. So now we will start at 3, 1. And if it makes more sense, if you're like, I would rather write my parent function and then go from that, go for it. So 0, 1, and then if 2 is raised to the first power, that'd be at 2. If 2 is raised to the second power, that'd be 4. Raised to the -1 is a half. -2 is a quarter. So you're just going to literally take all of these points and move them to the right 3. So go ahead and do that, and then let's move on to the next type of function. Okay, we have a couple more to go over. Okay, the equation for the parent function of the absolute value would be y is equal to the absolute value of x. And if we were going to graph this, for this parent function, your vertex would be at 0, 0. And then if you have 1 as x, the absolute value of 1 is 1. All right? The absolute value of 2 would be 2. Absolute value of 3 would be 3. And then the same thing is going to happen on the left side. And what's different between this and a quadratic function is that you end up forming a v with your absolute values, not a u. The domain would be all real numbers. Your range would include 0 and go to infinity. If we're going to write a child's function that is translated 4 units left, we're going to take y is equal, and we have the absolute value sign. Now left and right go inside the absolute value sign. And if it's left, it would be addition. So that would be translating it 4 units left. If we want to translate the parent function 6 units down, we would take the absolute value of x, and up and down get added and subtracted outside of the absolute value. Down would be subtraction, and we would do 6 there. How can you identify an absolute value function? It has a V shape. There's a constant rate of change for each side. So there's a constant rate of change on the right and a constant rate of change or slope on the left. And then it's symmetrical, so it has this axis of symmetry as well. A real-life example of an absolute value function could be, as Sammy walks to school, her distance from school decreases steadily. As she walks home, her distance from school increases steadily. And then it can ask, how is an absolute value function really a type of piecewise function? Well, you can say that it's made up of 2 lines that each have a restricted domain. Let's make this one a little bit harder. Let's do y is equal to, let's combine what we have up there. The absolute value of x plus 4, close it, and then subtract 6. Okay, well, the parent function is just simply this. So if we're going to move left 4 and down 6, this graph would look like so. The vertex would be at -4, 6, and then you can move every single dot, or in an absolute function, as long as it's not being stretched or shrink vertically or horizontally, you just go up 1 over 1, both directions. So the one below it would be this equation. Okay, last type of function that you learned was the square root function. The parent function with square root looks like y equals the square root of x. And if we graph specifically the parent function, we cannot have any x's on the negative side. So we're going to start at 0, 0, because when x is 0, the square root of 0 is 0. When we have x equal to 1, the square root of 1 is 1. Now, if x is 2, that gives you a bit of a messy number for y. So let's go and use perfect squares for the x's. So if x was 4, then you would have 2. And let's extend this. If x was 9, the square root of 9 is 3. So this is what your square root parent function looks like. The domain for this would be, yes, we include 0, and then we go to infinity. The range is the same. You include 0 and you go up infinitely. How can you explain how you got the domain and the range based upon your previous knowledge of square roots? Well, you know that you can only have positive numbers for x. And we'll write a positive radicand, which is the number underneath the square root sign. And then that's for your domain. For your range, you can only have positive answers to square root problems. All right. So what if we had a child function that is translated 5 units up? So 5 up. If it's up or down, the number is being added or subtracted outside. So y is equal to the square root of x, and then we're adding 5 because it's going up, and we're adding it outside. If we wanted to have the child function be translated, let's put this as, it says 1 right here. 1 unit to the right, then it would be y is equal to the square root, and right and left go inside the radical sign. So we're going to go x minus 1 because subtraction is moving to the right. 3 ways to identify a square root function can be the following. If it has a radical in the equation, if x is raised to an exponent that's a fraction, or if the graph looks like half of a sideways U, and I gave some examples to the right. Okay, so if we're going to construct a graph here, let's not use the parent function. We already did that. Let's combine these two. We have y is equal to, and let's actually vertically stretch it. Let's do 2 and then the square root of x minus 1 inside as the radicand plus 5. So the parent function, as we drew already, looks like this. Okay, so we're going to first, this means we're going to go right 1 and up 5. So if I go right 1 and up 5, then we would start here and it would go over 1, up 1, over from this point right here, over 4, up 2, and then over 9, up 3. Okay, but that's not actually correct because we need to vertically stretch by a factor of 2. So now instead of going to the right 1, up 1, we're going to vertically stretch that up 2. So this goes away. And if we look at this point, we went to the right 4, up 2. We'll still go to the right 4, but instead of going up 2, we're going to go up twice that amount. So up to 4. All right, and we can draw this now as that function right here. That concludes your notes for review on your different functions.